Hi everyone, I'm Deepak Sridhar. I'm happy to present our work on action localization in this year's ActivityNet Challenge workshop. Action localization via complementary learning and class semantic based attention mechanisms. This work is done by myself, Srikant Muralidharan, Yamal Kwadar, Yashin Lee, Peng Dai, and Joel Lu. We are from Noah's Ark Laboratory, Huawei, Canada. Our team secured the second place in the temporal action localization task. So to go into the brief introduction, action localization involves predicting the start and the end points in a video and also classify the action. So there are three main paradigms under which this is done. First one involves training frame level classifiers and then merging or smoothing the predictions to get the final proposals. The second one involves training proposal and the classification model separately and then combining them at the end. The third one involves end-to-end solution, which predicts and classifies the proposals directly from the untrimmed video frames. So our solution follows the two-stage approach where we train the localization and the classification model separately. So the end-to-end solution for action detection has not been promising as compared to the two-stage solutions. So we use the two-stage solutions in our approach. So the common practice for the two-stage solution involves the following three subtasks, where we first extract the features for the entire video, which is the representation for the videos. So this can be done using pre-trained video understanding models from different datasets. The second one involves proposal generation using these extracted features, which is the action localization. And action localization can be done using top-down and bottom-up approaches in the existing literature. The third one involves training the classification models to predict the action classes for each of these proposals. And the action classification system can be done using trimmed or untrimmed classifiers, which involves either trimmed clips or the entire video input. To go into our methods, so our solution involves exploring complementary aspects and then learn from the diverse perspectives. So we try to learn from the diverse settings for all the three components which is mentioned before. So for video feature encoding, we encode the video's features using diverse network architectures and learning settings. And for the action localization system, we use diverse components in order to learn complementary features and also use different subsets of the feature encoders. Some of the modules which we use include the attention modules and position encoding. And for the video classifier system, it usually involves learning from RGB and flow inputs and as well as from the aggregated trimmed classifier penultimate outputs. So the video classification can also be done with the different network architectures. So in our solution, so we employ a two-stage classification approach, which can be interpreted being complementary in terms of the input receptive field. So for the trimmed classification, we use input RGB or the optical flow frames for a trimmed part of the video. And for the untrimmed classification, we use the entire features for the whole video. So for the trimmed classification, we use the baseline model as the TSM ResNet 50, which achieves a single crop accuracy of 74%. So we improve this model by further using weight excitation and also using data augmentation from kinetics and HACS datasets. So this improves the top one accuracy to 80.6%. We also use other top models such as slow fast and coarse to find architectures together with the TSM ResNet 101 for flow features as well. For the stage 2 with the untrimmed classification, we use complementary sets of features to learn the classification representation using logistic regression, and also add attention models to that. We also tried different variants of transformer models, and we also use different complementary loss functions such as focal loss and weighted cross entropy losses. So in terms of extracting the complementary features from these trained action classification models, we extract class semantic rich output layer features as well as the penultimate features. So we use both RGB and flow based features. We also extract multi-scale features from these models, and we also use different action classification models such as low fast, X3D, Keras, something. In addition to that, we also used the recent publicly released TSP model, which is more localization rich features. And we also explore some self-supervised feature representations from multimodal versatile network features and MEL mass contrastive estimation features. So with regard to the action localization, most of the prior video feature encoding use this class semantic rich information in order to localize the actions. However, such features are not optimal for localization tasks, and so work such as TSP and BSP exploit that and train features for localization tasks. So our main research problem is that can we use these class semantic rich video feature representations to formulate an attention mechanism that can improve the action localization performance? Different from the prior works, we try to improve these features from the extracted pre-trained action classification models rather than using the new training methods. So our method involves attending to the input features for the action localization. So we propose an attention module that estimates the per class semantics and the per time step attention weights independently and applies them onto the localization encoder subnetwork. So such an attention mechanism can identify the temporal positions which are important for boundary detection based on these temporal variations of the class semantics. So an architecture of a proposed class semantic attention mechanism is shown here. Here we consider the system and decompose into three components: the feature extraction from the RGB or flow frames, and the localization base network, and finally the localization decoder, which involves predicting the start and the end points. So we apply our attention mechanism onto the localization encoder base network, where we apply the attention along the channel and the temporal axis. So this improves the features and it aligns more towards the localization tasks. And this method is generic, and so this can be integrated to prior action detection models. So since BMN is a high performing action proposal generation model, we use it as the baseline. So we apply the CSA attention to BMN to improve the detection performance. In addition to that, in order to further improve the localization performance, we consider these four perspectives, where we modulate the training methods, model parameters, model configurations, and using different set of features. So brief overview of our method is shown here. So for the loss functions, we try different loss functions, including contrastive loss, focal loss, learning to rank loss from object detection, and duration-based weighting for the IOU regression loss. In terms of model parameter tuning, we try different hidden dimensions and sample points and different depths for the base modules. And in terms of model configurations, we try different attention mechanisms such as relation-aware modules, position encoding, and our own class semantic attentions. And additionally, we also transform the input features into 2D and then obtain the attention weights using this CSA branch. So here we use 2D convolutions instead of 1D, and this operates on the local class temporal features, which provides more complementary outputs. And instead of 2D convolutions, we also try vision transformers such as VIT and Swin transformers. And for the feature encoders, we try different set of features extracted from different action classification networks, which was mentioned before. So in terms of ensemble approach, we do average ensemble of the feature map outputs. The weighted ensemble approach can give better results, but we observed overfitting with that. And the inference follows the standard BMN pipeline, where we multiply the classification and regression scores. In terms of post-processing, we use soft NMS for removing the redundant proposals with a threshold of 0.4. And we use the top 3 classification outputs for the final proposals. So in terms of results, our stage 1 ensemble yields around 90.68% top-1 accuracy, while stage 2 ensemble improves that to 92% top-1 accuracy. So here we list a different set of features which we use for classification models. So for the action localization, incorporating the CSA attention and the other variants which I described before achieves the single best state-of-the-art model of 39.16 using our classifier. And an ensemble of 30 of these variants achieves 41.74 validation MAP and 44.11 test MAP, which secures us the second place. To summarize, the second class classification further improves the ensemble and pushes the accuracy further. So for complementary aspect is essential for building the good ensemble, and good video features are key to that. Our class semantic based attention mechanism provides complementary outputs using the different variants which we described. And in terms of post-processing, tuning the hyperparameters can give some notable improvements as well. So we would also like to thank our collaborators who provided valuable inputs and suggestions for improving the submission. Thank you.